So we had the discussion yesterday about waves and their importance related to this. And now we want to make a connection between the wave motion. And again, we're not really going to try and understand the detail of the waves, these three-dimensional electron waves. We're not going to try and understand that detail of what that might look like, or how to view it, or anything like that. We're just going to say that it's a wave, and it takes up space around the nucleus. And if I add energy to that wave, it will increase the complexity of the wave. Okay, so that's how we're going to view this. We're going to say, I have a wave. My lowest energy level is going to represent a wave of the lowest level of complexity for an electron. And we're going to say that that takes up a certain amount of volume around the nucleus. And then if I add the right amount of energy, the amount of energy that would allow it to form a new standing wave at a higher energy, that means that its motion is going to be more complex than what it was at the lower level of energy. But what we want to do now is connect this wave motion to specific amounts of energy. Okay? If I have this amount of energy, I'm at the lowest level. If I have this amount of energy, I'm at the next level. And if I lose that amount of energy, if I go from this wave motion to this less complex wave motion, I'm going to release an electromagnetic wave of a certain amount of energy. And that certain amount of energy, oh, by the way, is the amount of energy between that lower energy level and that next energy level. So we're going to connect the electron wave motion to the quantization of energy. So remember that the observation is when an atom gains or loses energy, it can only do so in an amount that equals some multiple n of Planck's constant times the frequency of a photon of energy absorbed or emitted. Okay, so in a given electron, we're going to have a multiple of that that's going to represent the energy level. So 1 would represent the first energy level, 2 would represent the second energy level, and so on. Remember that HV is called a quantum of energy for that photon, and we're going to be multiplying it times an integer that we're going to call the quantum number. Now we can speculate, because it might be possible that our particle, the electron, moves with the motion of a wave. The absorption or emission of a photon of energy represents the right amount of energy to move the electron from a frequency representing one standing wave or mode of vibration to a different standing wave. And remember, we said that for a system, at least a two-dimensional system here, this represented the lowest amount of energy that would be required to create a standing wave, in which I would get 1/2 of a wavelength, and then the reflected wave would be the other half. And so the length of this, if it was a string, would be 1/2 of the length of the actual wave, right? The rest of the wave would be that. But whatever frequency it was that caused this first standing wave is the lowest amount of energy, or the lowest frequency that we can have that would give rise to a standing wave. And it's the same way with the lowest energy level. Okay? So, on the other hand, if photons of an amount of energy of other than 1, which would give the correct frequency, struck the atom, nothing's going to happen. Okay? If I get an energy that strikes the atom that would cause the energy to be somewhere in this range here, that would create a wave that would destroy my waves. It wouldn't create a standing wave, it would be destructive, so I can't use that energy. and that photon of energy would just pass on through the electron. Or it could possibly cause the whole atom to move faster. Okay? But it wouldn't change the potential energy within the electron or within the atom. It might do something to the atom as a whole, but it's not going to do anything with the potential energy inside the electron. Okay? Also, an electron cannot lose an amount of energy other than that which would give an allowed frequency. Okay? Now, remember, this is not the energy of the electron itself. Okay? This is not the amount of energy of the electron itself. It's the amount of energy change between frequencies of allowable energy levels, and so the amount of energy of the photon absorbed or released. So if I've got an electron here, and here's the next energy level, the electron itself has a certain amount of energy, and we don't actually know what that amount of energy is. We can't really measure that amount of energy. All we can measure is the amount of energy difference between here and here. We can only measure amounts of energy changes. We don't ever really know how much energy something actually has in it. We can only measure changes in energy. Okay, so if I have the right photon that comes in and zaps that, it could raise it to that energy level, and it would be at that energy level, but then it would fall back down and emit that same amount of energy. But whatever it is, that wavelength or that frequency of whatever that energy is would be added to that energy, would add to that and increase the frequency till there, and then it would lose that amount of energy and go back to that frequency. So, do all particles have wave motion? We've said that electrons have particle, or they're particles. They're particles that have a wave motion. Do other particles have wave motion? And we can talk about the wavelength of all particles. We previously used momentum to help us understand the particle nature of waves. Can we now reverse this reasoning to help us see the wave nature of particles in motion? So we're going to start with the momentum wavelength relationship. Remember, we said that the momentum of a wave, and if you needed this on the AP test, they would give this to you, but the momentum of a wave is equal to the Planck's constant, either divided by the wavelength or multiplied by the frequency divided by the speed of light. Okay, if we isolate the wavelength now, we get Planck's constant divided by momentum, and we recognize that in this circumstance we're dealing with particles that do have mass. If I have an electron, electrons have mass, right? So I have a particle that has mass. So change the momentum term into one that contains mass, and the momentum term for mass is mass, or for the momentum term that contains mass is mass times velocity, right? We said that momentum equals mass times velocity. That's a standard physics equation. And in this case, the velocity we're talking about is the speed of light. So we'll use c there instead of that. And the formula shows that if particles of matter do in fact have a wave nature, this would be how we would figure out what that wave nature is. Okay, we just created a formula for that. If I have a particle that has mass and that particle has a wave nature, this is how we would figure out what the wavelength of that particle is. So that gives rise to the question, do I as a human being have a wave nature? Okay, what's my wavelength? How do I vibrate as a wave? And as odd as this sounds, pretty much everything does have a wave nature too. This formula shows that if particles of matter do in fact have a wave nature, this would be how to determine the wavelength. There's another way to obtain this formula that really shows how interrelated all of these concepts are. It's one thing to do that and say, well, okay, I see that you've created this formula that suggests that particles do have a wave nature, but can you show me a little bit more proof of this? And if we start with the idea of mass-energy equivalence, sorry about what's going on there. That usually means my computer's starting to run out of memory. Start with the mass-energy equivalence, right? I've got energy that equals mc squared, and I've also got energy that equals Planck's constant times the frequency of a wave. And I can set these things equal to each other because E is equal to E, and I can come up with the same relationship here by manipulating this. I can remind myself that we're going to say that frequency is the same thing as speed of light over wavelength. And if I've got both of these on the same side of the equation, that can now say the C is going to drop out of both sides, and now that just gives me mc equals Planck's constant over wavelength, or I have wavelength equals the nature or Planck's constant over mass times the velocity. And so I've got two independent formulas that say the wavelength of a particle is this. Now, we still don't really know what that means, right? We just are suggesting that particles or things with mass have a wave nature. So the velocity we're talking about for the photon is the speed of light, so it's appropriate for the velocity term in the second equation to be c. But depending on the particle, especially if it has mass, the velocity is probably not going to be the speed of light. In fact, it's certainly not going to be the speed of light. So the more general form for this just uses the velocity term. And this formula applies to all particles in motion, even particles like baseballs and planets and galaxies. It turns out that all particles in motion travel in the form of a wave, no matter how massive they are. And we'll clarify this here in just a second. Now, this wavelength predicted by this equation is called the de Broglie wavelength. De Broglie was a graduate student at the time of his discovery, and it won him not only his PhD, but also a Nobel Prize. Imagine being a graduate student and winning a Nobel Prize. But he was the one that asked the right question. If waves can have a particle nature, can particles have a wave nature? So, compare the wavelength for an electron traveling at the speed of 1 times 10 to the 7th meters per second with that for a ball with a mass of 0.1 kilograms traveling at 35 meters per second. Okay, and so we're going to find out what the mass of these things is. Remember, the mass or the wavelength equals h divided by mv. Let me just make sure that that's right. Yeah. H divided by mv, and so this is going to be 6.626 times 10 to the negative 34th joule seconds divided by, for this, 1 times 10 to the 7th meters, and, or meters per second for the velocity, I'm sorry, times, and times 9.11 times 10 to the negative 31st kilograms, Electrons are tiny. So if I could get someone to actually calculate that for me. And I can think about this in exponent terms. 7 plus negative 31 is going to be negative 24. So negative 34 minus negative 24 means that I'm going to be somewhere in the range of 10 to the negative 10th.
How about 7.27 times 10 to the negative 11?
Okay, so that's pretty close to 10 to the negative 10th. 7 point how much?
27.
Okay, and then if we do the other one, 6.626 times 10 to the negative 34th joule seconds divided by 0.1 kilograms times 35 meters per second.
.31 times 10 to the negative 31st.
Okay, and so for the electron, the wavelength, notice the wavelength, it's about 10 to the negative 10th. That's a little bit smaller than nanometers. Nanometers are billionths of a meter, right? That's a little bit smaller than nanometers. And notice that this is about the size of an atom itself. Okay? This is in the range of the size of an atom itself, 10 to the negative 10th meters in diameter. Okay? But notice how tiny this wavelength is, 10 to the negative 31st. That wavelength is so tiny. Did you get a different answer?
Yeah, I think hers makes more sense too, because mine it shouldn't be the 31st, because the ones down below don't have any. So I think Emma's is right. She got 1.8 something times 10.
1.89 times 10 to the negative 34.
Yeah, I think.
Okay. So, and that's so 0.1 times.
I did the right numbers, or did you do them wrong?
So 10 to the negative first times 10 to the first is going to be 10 to the 0. So it should be in the range of 10 to the negative 34th, shouldn't it?
Yeah, no, she's right.
Okay.
Mine was in normal, not scientific.
Okay, so what did you get? 1.89 times 10 to the
negative 34.
Okay. Okay. So, and this is in meters, right, for wavelengths. So this is about the size of an atom, but this is incredibly, incredibly small. It's smaller than we could ever possibly hope to think about. And what we come to the conclusion of is well, and I'll get to a conclusion here about this, what this really means in just a minute. I want to move on just a little bit from this. For right now, recognize that the wavelength of an electron is about the size of an atom, but the wave of things that are more massive gets smaller and smaller and smaller. Okay, the wave of things that are more massive gets smaller and smaller and smaller. Okay, and that means a higher frequency, right? So note, the wave motion of the electron should not be confused with the wave motion of the energy it may absorb or emit in changing energy states, right? The electron itself has a wave motion that's related to the nucleus, okay, has a wave motion that's kind of related to the nucleus, okay, but the wavelength of energy that jumps that from one level to another level is something that's different, right? So don't confuse the wave motion of the electron itself with the wave motion of the energy it may absorb or emit changing energy states. Now, that all particles in motion have wave characteristics probably doesn't seem to make sense. If someone throws a fastball, do we see it traveling with a wave-like motion? We don't, do we? Okay? However, if we consider the size of the object in comparison to the size of its wavelength, we can at least gain a partial understanding. For the baseball, we calculated the wavelength, you were right, Emma, of 1.89 times 10 to the negative 34th. In comparison to the size of the baseball, this is an incredibly small value. So while the baseball exhibits both particle and wave features, because the wave nature of it is so small, we only see the particle features. Okay, and that's the way to look at this. What is the nature of the particle feature versus the nature of the wave feature? And the bigger the particle is, a baseball or a planet, the smaller its wave is going to be, and so the more the particle nature dominates, and that's what we observe. On the other hand, the radius of an electron is on the order of 10 to the negative 15th meters. Its size is about 1,000th of the length of its wave. Okay, so the electron's radius is about 10 to the negative 15th meters. It's smaller than the length of its wave. The baseball's a lot bigger than the length of its wave, so we see the particle nature. The electron is a lot smaller than the length of its wave, so we see the wave nature. Okay? Therefore, its wave nature determines much more of its behavior, and it follows the rules of needing to form standing waves when constrained in an atom. Okay? Now, the final proof of the wave nature of particles, in addition to measurable properties of waves we're already familiar with, electromagnetic radiation exhibits the other major behavior of waves: refraction, diffraction, and interference. And we'll explain what we mean by those. You've probably heard these terms before, though. Like all waves, the speed of electromagnetic radiation changes when it enters a different medium. And your best example of that is when light enters a glass of water, it changes its direction. Okay, you can tell that because if you put a straw in water, the straw appears to be broken, doesn't it? When you look at it in the air versus the water. If electromagnetic radiation passes into a denser medium, although velocity stays the same, frequency stays the same, wavelength will decrease, causing the velocity of the wave to decrease as well. Remember, the velocity of the wave equals the wavelength times the frequency. So the frequency of the wave is going to stay the same when it goes through a different medium, but in order for me to decrease the velocity, I'm going to have to decrease the wavelength. Okay? If the wave passes into the new medium at an angle, this change of velocity occurs only as each part of the wave comes into contact with the new medium. So when I have a wave that comes into contact with a new medium, and I've got an electromagnetic wave here coming into contact with the glass of a prism, and if it comes into contact with it at an angle like it is here, the first part of the wave, we have something called a wave front. The first part of the wave contacts, and let me draw that a little bit differently. The first part of the wave contacts this part of the glass first, and this part of the wave slows down first, whereas this part of the wave keeps going faster. And this part of the wave slows down. So what it essentially does is it kind of grabs a hold of that wave front and causes it to turn as I go. And it's no longer going this direction, it's going this direction when it comes into the prism there. And this effect is called refraction. If the new medium is represented by the glass of a prism, the wave will be bent toward a line that's perpendicular with the surface of the prism. Okay? And you don't really need to know these details. Upon reaching the opposite side of the prism, the individual waves will speed up again and be bent and spread even further apart. So if I have white light, I have light of different wavelengths smacking the prism, it's going to bend the different wavelengths of light at different ways. So the shorter the wavelength of light entering the new medium, the more it will be affected. So red light with a wavelength of 750 nanometers is not going to be as affected as much. It's got a longer wavelength, so it's not going to be as affected as much as violet light. So red light is going to be refracted less, while violet light's going to be refracted more. And it's going to cause the different wavelengths to be spread out, and that's what we see when white light passes through a prism. Therefore, if white light, which is a combination of all wavelengths, has passed through a prism, the prism separates the colors present. This phenomenon is called dispersion. Another thing that happens to waves if they pass through a barrier here, the bending, diffraction is the bending of waves passing an obstacle. If a wave has passed through a slit that is about the same size as the length of the wave bends equally around the edges of the barrier here, and it causes a circular wave to be formed. So this is a plane wave that smacks the barrier, and the part of the wave that goes through the slit here get bent around the edges of the barrier, and this is called diffraction. And then if waves become superimposed on one another, their amplitudes can add together in a process called interference. If the amplitude of both waves is positive, this is called constructive interference. If the signs of the amplitudes are opposite, the waves will partially or completely cancel each other out, and this is called destructive interference. And this process can be demonstrated by sending a single wave through two slits. So I've got a wave that passes through these two slits here, and they're going to get bent into this circular wave at each of these points, and then these circular waves are going to smack into each other, and where the waves interfere constructively, we're going to get patterns of more light. Where they interfere destructively, we're going to get patterns of no light. Okay, so this is called an interference pattern. As the semicircular waves travel outward from both slits, the two semicircular waves will interfere in the middle, creating a complex pattern of interference as waves alternately constructively then destructively interfere. Now, here's the proof that I was talking about. The final proof that electrons have a wave nature, if you're still not convinced. And this would be a piece of information that you need to know. Yeah. Sorry about that. This would be a piece of information that you need to know. If particles like electrons really do behave in a wave nature, we should be able to get them to diffract or bend around a slit like any other wave. The problem was finding a slit that approximated the wavelength predicted by de Broglie, about 10 to the negative 10th meters. If I want to see diffraction, my slit has to be just as small as the wavelength. And the wavelength of the electron was supposed to be about 1/1000th of a meter. Well, where do I find a slit that is 1/1000th of a meter wide? So Davison and Germer considered that the space between atoms in a crystal was similar to this. Okay, so if I remember that I have atoms that are stuck together in crystalline structures, like sodium chloride, okay, or just any kind of solid that's in a crystalline structure, there's going to be some space between the atoms, and they thought that the space between the atoms would be about the size of the wavelength of an electron. And they demonstrated that passing a beam of electrons through a thin crystal of nickel caused a diffraction pattern. Okay, so they proved that the electrons could be diffracted, and that showed that they were in fact predominantly waves. So a pattern of interferences of waves passed through numerous slits. So that was the final proof. Okay? Any questions about that? That's a long-winded way of getting to the point that the final sort of proof that electrons behaved as waves, and now we have this information that they behave predominantly as waves because their size is smaller than their wavelength. So we see the wavelength, and again, that's how you have to think about it. Everything has a wave motion when it's traveling. Travels in a wave motion, but most objects that we can see, their wavelengths are so small that the particle nature predominates, and we just see the particle. Okay, we just see the baseball going to the catcher's mitt. We don't see it traveling as a wave. Okay, and this was the final proof of that, this diffraction pattern. So that would be the piece of information that's important there. Now, once we started to think about this and understand that the energy inside of atoms had to be quantized, how did that help us figure out what the structure of the atom is? Okay, we figured out these things had to be quantized, but we still didn't even know really that much about electrons. We'd only just discovered electrons. We had figured out that there must be protons. We figured out there must be neutrons as well, but we didn't know how the electrons were arranged around the nucleus or within the atom, and we want to know something about that. And the atomic spectra that we were starting to be able to consider gave us some more information about that. So another piece of information consistent with the quantization of energy. Remember, we said that if white light is passed through a prism, it provides us with a continuous visible spectrum. You've all seen what light passing through a prism looks like. It's that nice, pretty rainbow, right? Light emitted by heating sources of atoms of individual elements provides a line spectrum. What do we mean by that? When atoms of individual elements are heated, the provided electromagnetic energy is absorbed by electrons in the atoms, raising them to a higher energy state, right? We know this means now that what we're doing is we're not really raising it to a higher orbit. Yeah.
We don't have that page. And our packet's ending anymore.
Dang. I forgot that we were going to. So they end after 21? Yes.
Yeah, 21 is our last page.
How many pages do we have altogether? Well, let's just print to the page. Okay. Sorry about that. A little break. This is hard. It's all conceptual and there's not a lot to hang your head on. So, I'll be right back.
I heard you.
Thank you.
Sure. Oh, here.
I suppose you need those.
Of course.
Where do you want the
Just sit there. Okay, so again, we recognize that what it really means is that when I jump from one energy level to another energy level, I'm not really moving further away from the nucleus. I'm changing my motion to a more complex, higher energy motion, right? Okay? And be aware that all of these electron waves are simultaneously in motion around the nucleus. If I have more than one electron in the atom, they're all occupying this same space. Okay? And that we'll find out that the more electrons I have, this affects the nature of the space that the electrons can sit in. Okay, so if I go to this higher energy level, that takes more energy to maintain, so it's a less stable state, and the electron will return to a lower energy level. And when this happens, a photon of energy equal to the frequency of the energy lost radiates from the atom. Because frequencies at which electrons can vibrate are determined by the constraints of the type of atom. Remember, each atom has a different number of protons, a different number of neutrons, a different number of electrons. And so you can imagine that that system for each specific different type of atom is going to dictate different frequencies at which these electrons can vibrate. It's not going to be that the hydrogen electron vibrates at a certain frequency and then that electron in a helium atom also vibrates at that frequency, right? When I get to the helium atom, I've got 2 protons and 2 neutrons and 2 electrons. And the constraints of that are going to be that the vibrations are different for standing waves for those electrons. Okay? And if we have drops from one energy level to another energy level, because the frequencies at which the electrons can vibrate are determined by the constraints of the type of the atom, the transitions in energy that the electrons can undergo will always be the same for the same type of atom. The electron in the hydrogen atom will always undergo the same transitions. The electrons in the helium atom will always undergo the same transitions. And we can see if in the visible spectrum, or detect in other ways, if it's UV or IR, the frequencies emitted. Okay? So it should make sense that each different atom, if I heat it or add energy to it, it's going to emit electromagnetic radiation that we can detect, and that's going to be a signature for that atom. Okay? It's going to give up its own distinct set of energies. So because these transitions represent single wavelengths of light, we identify them as lines along the electromagnetic spectrum rather than as the continuous spectrum of white light. And so this gives us something called a line spectrum. And this isn't in color, but for example, this is mercury, and these numbers are actually in angstrom units. That's 10 to the 9th. Nanometers would be 10. I'm sorry, that's 10 to the 10th. Nanometers would be 400 nanometers here instead of 4,000 angstroms. 450 nanometers. So I've got in mercury, I've got a ray of light that's emitted at about 400 nanometers and a little higher than that. And we have all of these different light wavelengths or frequencies that are emitted for mercury versus lithium versus cadmium versus strontium versus calcium and sodium. Okay, so we have these different types of spectra. Okay, and we call this a line spectrum, and the pattern of lines is specific to the atoms of the element being heated, and in general is more complex the more electrons there are, because there are going to be a greater number of transitions. Now, you have to realize that an electron doesn't just have the option going up one level and then coming back down. So for example, in a hydrogen atom, I might do that. Okay, I might jump from the lowest energy level, and that's its natural state too, right? The hydrogen atom, the ground state, or the lowest possible state, is the most stable state. So that's where you're usually going to find these electrons. But I could jump to here and then back down, or I could jump all the way up to here and then back down to here, and that would be a different color of light than jumping back down to here. Or I could jump all the way up to the fourth energy level and back down to the third, or I could jump from the fourth to the second, or I could jump from the fourth to the first. Okay, and so all of these would have their own characteristic different radiation wavelength. Okay, so for hydrogen, even with just one electron, I expect a bunch of different frequencies in my line spectrum. If I get to an atom with 10 electrons or 100 electrons, I'm going to have massively more complex spectrum. Okay, and we can see these things. And I can show you how. So we have these things called spectrometers. Some of them have lost their. Take one of these. That's what you do. And we can, for example, look at our and you're going to hold these. It doesn't really matter whether you hold it one way or the other, but you look through this end and you point this towards the light, and you can see either to the left or the right of the white line in the middle there, a pattern of colors, right? Okay, and in fact, you can see a little scale off to one side that accompanies that, and that will tell you, and my eyes can't quite read that. Let's put glasses on. Okay, so I got mine upside down. So if you want it right side up, the scale should be to the left. And if you look directly at the light, you'll see that there's a red line. And where about is that red line at as far as the scale goes? If we're looking at this.
6.25.
Okay, so it's in that 600 range, isn't it? Okay, and we said that infrared was at about 750, right? So that's close-ish. My glasses are all steamed up here and aren't letting me see anything. Then we see a green light, or kind of an orange line at about 600, and then a green line at about 560 maybe.
Give or take, yeah.
Kind of a blue line at a little bit more than 500, and then a violet line at about 450. Okay, so these lights are mercury lights. They're fluorescent, and we should see things similar to that. And so there's a line at about 450 for mercury, and then this isn't corresponding exactly to what we see, but there's the red line and there's the orange line, and maybe there's the green line, and then or maybe that's the blue line. But it's a similar kind of a spectrum. 1, 2, well, we should see a big line there, so maybe that's the green line. and then the blue line, and then the violet line. Okay, and these aren't good enough to resolve those three lines there. Okay, so they're really, really, really bare bones. They're not great quality, but they at least let you see some of these things. And this is a line spectrum. Okay, and the pattern of lines is specific to the atoms of the element being heated, and in general is more complex the more electrons there are, obviously. And we can create light from various elements by placing gas of that substance in a tube and firing electrons through the gas to cause energy transitions, and this is called a gas discharge tube. The color of light given off will be a combination of the strongest lines. So what we actually see as the light of this fluorescent light here is the combination of those 5 lines, those 5 colors, right? It's not just white light, it's the combination of those 5 colors that gives us this kind of a white light. Okay? So we might get a chance to play around with these a little bit more at some point as well. But anyway, we have spectra for all of these. And I've said here, notice that the wavelengths of the line spectra above are given in angstrom units. They're typically displayed from shortest to longest wavelength in contrast to how we view the electromagnetic spectrum, right? Normally we view the electromagnetic spectrum with wavelengths increasing to the left. But this thing has wavelengths increasing to the right. Okay? And that means the lower frequencies are to the left. Right? The lower frequencies are to the left. And if we have nanometers here of visible light, the higher energy is going to be to the left, and we're going to the right with the lower energy. And for most spectra, the transitions of electrons will give us energy or give us lines in the ultraviolet series, in the visible series, and in the infrared series of light. Okay? So if we look at hydrogen's spectrum, hydrogen has only 1 electron, so it's going to be the easiest for us to look at, right? It's going to have the lowest number of transitions. And they were the first to be used to point to a possible structure for the atom based on energy transitions. Okay, so what we saw is that we have an ultraviolet series, we have a visible series, and we have a infrared series. And the Lyman series, or the ultraviolet series, this was the guy that discovered them or described them. Each of the lines represents the frequency of light emitted when an electron moves from an outer level to the first energy level. Okay, so if I have electrons falling from an outer level to my lowest or my ground state energy level, I'm always going to get ultraviolet radiation. That's going to be the longest drop, right? This is going to be the longest drop that I have, so I'm going to get the most energy, and it's going to have the highest frequency or the lowest wavelengths. So we see that if I go from the second energy level to the first energy level, I give off a wave of 122 nanometers. If I go from the second level to the first, a wave of 103. From the fourth to the first, and you don't need to know these by any stretch of the imagination. You just need to be aware that if I transition from an outer level to the first energy level, I'm probably going to get ultraviolet light. Okay? If I transition from an outer level to the second energy level, I'm probably going to get visible light. And if I transition from an outer level to the third energy level, I'm probably going to get infrared light. Okay? Now, if I just look at the ultraviolet series here. Each of the lines represents the frequency of light emitted when an electron moves from an outer level to the first energy level. As longer wavelengths represent lower frequencies and lesser energies, you would expect the longest wavelength to represent the transition from level 2 to 1, and each successive shorter wavelength to represent the transition from a level further out. Okay, and we can confirm this. And notice this data here that we have. Going from the second energy level to the first energy level, okay, level 2 to level 1, I have a wavelength of 122 nanometers. This is this frequency, right? And if I go from 3 to 1, I'm going to have a greater energy release, right? I go from level 3 to level 1, that's going to be more energy, so I'm going to have a greater frequency and a lower wavelength. If I go from level 6 to level 1, I'm going to have a yet lower wavelength and a higher frequency. And then if I finally get kicked out of the atom, or if the atom captures an electron from outside the atom and it goes to the lowest energy level, this is the amount of energy I'm going to release, and that's the wavelength that I would get. Now, as the wavelength for each line becomes shorter, what happens to the frequency of the wavelength? As this gets shorter, what happens to the frequency?
Increases.
It increases, and that's what it's supposed to do, right? The shorter the wavelength, the greater the energy, the greater the frequency. It's harder to move that many beats, right? What happens to the energy released in the photon for that wavelength? If I go from longer wavelength to shorter wavelength, what happens to the amount of energy that's released?
It decreases.
Okay? I would argue that it increases, but in a negative direction.
I guess.
Okay? So we're going to have to make a distinction here. This negative number is going to refer more to a direction of energy flow rather than an absolute amount. Okay? We need to think about this in an absolute amount, and the negative sign means that the energy is lost. Okay? The energy is lost. Okay? So the energy is lost. And if I go the opposite direction, if I go from level 1 to level 2, and I'm not going to have a wavelength, right, because it's not going to be emitted, it's going to be absorbed. If I go from level 1 to level 2, I absorb this amount of energy. If I go from level 1 to get kicked out completely, I absorb that amount of energy. Well, notice that the amount of energy that I absorb to get kicked out of the atom is the same as the amount of energy that I release when I leave or fall back. Now, because energy is lost by the system when an electron moves to a lower energy state, we represent these as negative values, okay? And again, the negative value doesn't mean I have a smaller number. It means I have a larger number at a loss, right? So the energy required to accomplish the opposite transition is the same, but positive instead of negative because the energy is absorbed. Now, what do you notice about the energy required to push an electron further and further away from level 1? What do I notice about the energy that's required to push an electron further and further away from level 1? If I go to level 1, I gain this much energy. If I go to level 2, or if I go to level 2, to level 2, I gain this much energy. Level 2, what do you notice about the increment of energy?
Let's see, that one increases. No.
Okay, so what do you notice about the increment here? From here to here, I gain about 0.3 times 10 to the 18th, negative 18th joules, right? If I go from here to here, I gain about 0.15 or 0.11. If I go from here to here, I gain about 0.5. If I go from here to here, I gain about 0.2. If I go from here to here, I gain less than 0.1. So the amount of energy that is required to go to the next level decreases. Okay? To go from level 1 to level 2 takes a fair amount of energy. But to go from level 1 to level 3, the increment there is not quite as much, and the increment is not quite as much, and the increment is not quite as much. So what we can say is, what do you notice about the energy required to push an electron further and further away from level 1? It decreases, right? Why might that be? Why might it take less energy or an increment of less energy to go one energy level further and one energy level further?
Because it's further away from the nucleus, and so there's less force of attraction holding it in place.
Okay, that's exactly right. I've got protons in the nucleus, right? But if I get further away from the nucleus, it's going to take less energy to go to that next level and less energy to go to that next level. So why might this be? Because increasing distances from the nucleus, or the positive charges of the nucleus, right? It takes less energy to get kicked further and further away. And then finally, I give it that last little bit of energy, and the electron is completely lost to the atom. Okay? That's the energy of ionization. Okay? Now, how is this reflected in the distance between lines in the spectrum? What happens as I get further and further away from the nucleus? This is the first line representing the first transition. This represents the next transition. This represents the next transition. What happens to the lines in each of these series as I get further and further away from the nucleus?
Sweet. Well, I want to say they're more spaced out, but then there's the clump at the beginning of the infrared.
Okay, but that's what I'm asking here. As I get further away from the nucleus, what happens to the spectral lines? They get closer together, right? That's reflecting the fact that it requires less energy to move that further away. We're about out of time, aren't we?
Yeah.
Is this making any sense at all?
Yeah.
It's a little fuzzy, though, probably, but hopefully it's going to make some sense. Okay? And if you understand this, it's going to make your understanding of atomic structure a little easier. Okay? We'll keep banging away at this.
Are we having a test by chance?
Not before break, no. It'll be
Take home?
yeah, there'll be some kind of take-home assignment. I need to start evaluating you guys in some way or giving you more homework or something. I'm really struggling with, 6 classes and trying to do online and in class at the same time.
Yeah, I understand.
So please continue to bear with me.
All right.
But all of these things are now online. So
Where do you want the, I forgot what you call these.
spectrometers.
Yeah, spectrometer.
You can just put them back up here on my table.
All right. Like thinking like spectrums here, I'm like, no, that's not right.
They might actually give you credit if you put that on an AP test. Spectrum seer.
Spectrums here.
See you guys later.
Yeah.
See you later.
Have a great day.
Take care.
Thanks, Dr. Marshall.
See ya.
Thank you.
See ya.
Dr. Marshall, I finally finished it.
Good, thank you.
Yeah, of course.
You're awesome.
Thank you so, so much.
Is what we're doing in our labs making any sense?
Yes.
Good, good.
I have a note for you. It just dropped.
I'll start.
No, you're perfectly fine. I will tell you.
Okay,
Okay, thank you so much.
thank you so much.
Have a good rest of your day.
Take care.
You too.
Hi, Brooklyn.
Hey, I was from Jen's room talking about POSA.
Yeah.
Oh yeah, somebody tasted the copper sulfate in my group.
No, they didn't.
Yeah, they did.
Seriously?
They went like, yeah. Seriously. Yep. I was like,
Okay.
wow.
Well, I would need to see that in order for me to do something about it, but who was it? So I can watch it next time.
Yeah.
Okay.
Cool.
Thank you.
You're welcome. And then I emailed Mrs. Savage to see if we're still on for tomorrow after like 2:45.
Yeah.
Then I should be able to come to the thing on
On
Saturday.
Saturday? Are you looking forward to that?
Yeah, I need to ask my mom. I don't think I have anything on Saturday, but
Okay.
who knows?
Okay.
Cool. I'll see you later.
Take care, Brooklyn.
I will see you.